It's kind of amazing, isn't it, how much our modern world really runs on lithium.
Hmm. Batteries, EVs, it's fundamental now.
Exactly. But how do we actually get it? Today, we're diving into something called spodumene flotation. You've pulled together some really cool research on this.
That's right. And it's quite a mix of papers, looking at it from different angles, chemistry, physics, engineering. It really shows how layered this topic is.
Definitely. So for everyone listening, our goal today is basically to unpack spodumene flotation. We'll look at how it works, what the big challenges are, and some of the cutting-edge stuff researchers are doing to improve it. Think of it as your shortcut to understanding a pretty vital process.
And the sources cover a lot of ground. We've got studies on like the very first step, grinding the rock and how that affects things. Then there's the surface chemistry, the chemicals they add.
Collectors and depressants and things.
Exactly. Activators too. And even computer simulations trying to model what's happening at the atomic level. It's pretty comprehensive.
Okay, let's jump in. Spodumene flotation. It's the main way we concentrate lithium from the ore, but it sounds like it's not straightforward.
Not at all. The biggest hurdle is separating the spodumene, that's the lithium mineral, from all the other stuff it's mixed with.
The gangue.
The gangue, right. Things like quartz, feldspar. And the problem is their surfaces can be chemically quite similar to spodumene.
So it's hard to tell them apart chemically, like trying to sort slightly different shades of gray pebbles?
That's a decent analogy, yeah.
Hmm.
So flotation aims to make the spodumene hydrophobic.
Water repelling.
Exactly. So it hates water, latches onto air bubbles that are pumped through, and floats to the top. The gangue minerals, ideally, stay hydrophilic, water-loving, and sink.
Okay. And that's where collectors come in, chemicals that help this happen.
Precisely. Collectors are molecules designed to selectively attach just to the spodumene surface.
Ah.
Common ones are sodium oleate people, often just say NaOL or another called DDA. When they stick to the spodumene, they make its surface hydrophobic.
Got it. They give the spodumene its little life jacket to catch the air bubbles. Okay, so step one is this chemical targeting. But the sources stress that even before that, the grinding is super important. I wouldn't have guessed that.
Oh, absolutely critical. How you crush the rock has a massive downstream effect on flotation.
How so?
Well, the research shows that even what the grinding mill itself is made of matters.
Really? Like a steel mill versus something else?
Yeah, or like corundum versus nylon mills. The papers mention those specifically. They can lead to different flotation results.
Wow. What?
It seems to be about tiny amounts of metal ions getting onto the spodumene surface during grinding.
From the mill wearing down.
Could be from the mill, yeah. Little bits of aluminum, iron, whatever the mill contains. Or it could be ions coming from impurities already in the spodumene crystal itself being exposed or mobilized by the grinding. We're talking Al, Cam, Mg, Fe, even Li ions.
Huh. So the crushing machine literally becomes part of the surface chemistry. That's wild.
It is, and there's this fascinating experiment mentioned where they've tried acid pickling.
Acid pickling. Like cleaning it.
Essentially, yeah. They used acid to wash off these surface metal ions from the ground spodumene. And guess what?
The flotation tanked.
Totally. Really poor flotation response. Didn't matter how it was ground initially. It strongly suggests those surface metal ions are somehow crucial for the collector to attach properly.
Okay, so surface contamination or maybe activation from grinding is key. But it's not just the chemistry, it's the physical shape too. The size and flatness.
Right. Particle size and shape definitely play a role. One study found, for instance, that a big corundum mill made particles that were finer, but also longer and flatter.
Compared to
smaller corundum mills or nylon mills, which tended to produce more sort of flaky particles.
And why does that matter? More surface area.
Partly more surface area, but also which surfaces are exposed. Spodumene crystals have preferred ways they break cleavage planes.
Like fault lines in the crystal?
Kind of, yeah.
Yeah.
The main one is called the 110 plane. Different grinding might expose more or less of the specific plane, or other planes like the 001 plane.
And different planes react differently with the collectors.
That's the idea. Research, including simulations we'll get to, suggests collectors like NaOL prefer certain planes over others. So how you break the rock influences how well the collector can grab on.
Okay, this is getting complex, but really interesting. You mentioned ions coming from impurities inside the spodumene, too, not just from the grinding mill. Lattice impurities.
Yes, exactly. Even pristine-looking spodumene isn't perfectly pure chemically. It can have other metal ions that snuck into the crystal structure as it formed millions of years ago.
Built-in imperfections.
Right. And the computational studies, using density functional theory, or DFT.
Those super detailed atomic models.
Yeah. They suggest that iron, Fe and calcium, Chi, are quite likely to substitute for aluminum atoms within the spodumene lattice. Magnesium Mg seems less likely to fit in that way.
So naturally occurring iron and calcium inside the crystal structure, and that affects flotation.
It seems so, particularly iron. The research points to these substituted iron sites being really important active sites for sodium oleate to adsorb onto.
So the collector actually targets these impurity spots.
It looks that way. And energetically, the DFT calculations show that Fe substituting for Au is the most favorable substitution, which kind of makes sense because iron-bearing spodumene is pretty common geologically.
Wow. A tiny impurity becomes a crucial docking point for the collector. That's amazing. What about vacancies, like missing atoms?
Good question. The models also looked at that. What if a lithium or aluminum atom is just missing from its spot in the lattice?
Yeah.
Well, the calculations indicate these vacancies, especially if they're right on the particle surface, can dissolve pretty easily when in contact with the flotation solution.
And that would change the surface.
Potentially, yes. It could alter the local chemistry right where the collector needs to attach, which could, impact the flotation efficiency.
Okay, so we've got grinding effects, surface ions, internal impurities, even missing atoms, all influencing things. Now let's talk more about those chemical tools. We know about collectors like NaOL. How do we make them work even better? Activators.
Right. Sometimes NaOL on its own isn't quite selective or strong enough. So you can add activators. These are often metal ions. Things like iron ions, Fe3+, calcium, San2+, magnesium, Mg2+, maybe even lead, Pb2+, are mentioned.
And you add these deliberately.
Yes, in controlled amounts. The idea is they react with the mineral surface first, kind of priming it, making it more receptive to the collector, attaching strongly and selectively.
Like a chemical handshake before the main event.
Yeah, something like that. One study showed adding F3+ ions really boosted spodumene recovery, but you had to get the dose and the pH just right. Too much or wrong pH, and it might not work or could even start floating the gangue.
Tricky balance. And I saw mentions of using collector mixtures, not just one type.
Yes, that's another strategy. Sometimes combining different types, say an anionic collector like NaOL, with a cationic one or with a non-ionic one can give better results than either one alone.
Why is that? Teamwork.
It's thought to be synergistic. Maybe they pack better on the surface together, or one helps the other attach, leading to stronger hydrophobicity or better selectivity against the gangue minerals. The exact mechanisms are still being researched, but mixing collectors can be effective.
Okay, so we're trying hard to make the spodumene float, but just as important is making sure the other stuff, the quartz and feldspar, sinks.
Depressants. Wow.
Absolutely vital. If you float everything, you haven't achieved separation. Depressants are chemicals added to selectively make the gangue minerals hydrophilic, or at least prevent the collector from attaching to them.
So they stick to the gangue and say, stay down.
Pretty much. Common ones include things like sodium carbonate, starch derivatives like dextrin, special polymers like PISA, and one interesting one mentioned is CCS.
CCS.
Carboxylated chitosan. It's derived from chitin, from shellfish shells.
Seriously, chitosan in mining. Yeah. The thinking is the carboxyl groups on the CCS molecule can chemically bind quite strongly to spodumene, potentially blocking collector adsorption there if used that way, or potentially binding weakly to quartz to depress it. The study suggested it chemisorbs onto spodumene, but has weak adsorption on quartz, making it a potential selective depressant for quartz. It's quite specific chemistry.
That's fascinating, using natural derivatives. Okay, so chemistry is key, but let's circle back to particle size. You said there's a sweet spot.
Definitely seems to be. The data often shows recovery peaks in a certain size range. One paper mentioned 38 to 45 micrometers as being optimal.
That's tiny, like fine dust or silt.
Very fine, yes. If the particles are much bigger, they might be too heavy for the bubbles to lift efficiently. If they get too fine, other problems arise.
Like what? Doesn't finer mean more surface area?
It does, but remember the crystal planes.
Ah, right. The 110 that collectors like versus others they don't.
Exactly. Initially, grinding finer might expose more of the favorable 110 surfaces. That's good. But if you grind too fine, you might start creating a higher proportion of the less favorable surfaces, like the 001 basal plane.
Because the crystal breaks differently when it's super fine.
Potentially. Or you just get more edges and corners relative to the flat faces. Plus, very fine particles can cause issues like slime coatings or just behave differently hydrodynamically. It's complex. This idea of different faces having different properties is called anisotropic surface properties.
Anisotropic, meaning not the same in all directions.
Correct. And molecular dynamics simulations back this up. They show nail molecules preferring to bind to that 10 plane, likely because it has more of those broken aluminum oxygen bonds that the collector head group can interact with.
So you need to grind just enough to liberate the spodumene and expose the good surfaces, but not so much that you create too many fines or expose the bad surfaces.
That's the balancing act, and is where those computational models become so useful.
Right, the DFT and molecular dynamics, they let researchers see these interactions.
In a way, yes. They let us model how atoms and molecules behave at that interface between the mineral, the water, and the reagents. You can calculate surface energies, see how a collector molecule actually sits on the surface, figure out the binding strengths.
Without having to do incredibly difficult surface science experiments for every single variable.
Exactly. It complements the lab work beautifully. It helps understand the why behind the experimental results. For instance, confirming that NaOL preference for the 110 plane through energy calculations adds a lot of confidence to the experimental observations.
It's amazing how computing power helps unravel these really fundamental industrial processes. Okay, so bringing this all together for optimizing the actual process, conditioning seems really important. That mixing stage before flotation.
Crucial. Conditioning is where you mix the ground or slurry with all the reagents, collector, depressant, pH modifiers, activators. How you do this matters a lot.
What parameters?
Things like the pH you adjust the slurry to, the dosage, how much collector you add, the conditioning time, how long you mix it, and even the mixing intensity, the power density.
So it's like baking a cake, get the ingredients and mixing wrong, and it flops.
Very much like that. The studies show you generally need higher collector doses for good lithium recovery. But then you need to manage the pH carefully to keep the gangue depressed and maintain the grade or purity of the final product.
And the mixing power? Too much is bad.
It can be. Too little mixing, and the reagents don't disperse properly, they don't contact all the particles, but too much mixing, very high shear, might actually break down the collector aggregates or structures that form in solution, which can be important for flotation. So it's an optimal power range.
Another balancing act. It seems the whole process is about trade-offs, especially between getting more lithium versus getting pure lithium.
That's often the core challenge. Maximizing recovery versus maximizing grade. Push too hard for recovery, and you might pull up more gangue, lowering the grade. Be too selective for high grade, and you might leave some valuable spodumene behind, lowering recovery. Finding the economic and operational sweet spot is key.
Wow. Okay, that was a deep dive indeed. Let's try and recap the big points for everyone listening.
Sounds good. So, spodumene flotation. Way more complex than it might first appear.
Definitely. We saw how the initial grinding is critical, not just size and shape, but even the mill material influencing surface ions.
Right. And then there are the inherent properties of the spodumene itself. Those lattice impurities like iron acting as active sites, and even vacancies potentially playing a role.
And the chemical toolkit is sophisticated. Collectors like NaOL to make spodumene float, activators potentially boosting them, and depressants like maybe even chitosan derivatives to keep the unwanted stuff down.
Don't forget, particle size being key, finding that optimal range to expose the right crystal faces like the preferred cloning plane. And computational modeling is really helping us understand why these things work at the atomic level.
And finally, putting it all together in the plant involves careful control over conditioning pH, dosage, time, mixing energy, always balancing that trade-off between recovery and grade.
Precisely. And understanding all this is just fundamental for efficiently getting the lithium we need for batteries and our energy future.
Absolutely. It really gives you a whole new perspective on that battery powering your phone or car.
Yeah.
So here's a final thought to chew on as we wrap up. Considering all this complexity, the chemistry, the physics, the engineering challenges, what might the next big leap in spodumene flotation look like? Is there a holy grail out there?
Maybe a single reagent that's incredibly selective, works across different ore types, and is totally environmentally benign. That would be ideal, wouldn't it?
Or maybe a completely different physical separation method. Who knows? It makes you think about where the research might go next, drawing on all the insights we talked about.
Indeed. And for anyone whose interest is piqued, the sources you shared really are a great starting point to explore mineral processing, material science, or just the future of these critical metals further.
It's kind of amazing, isn't it, how much our modern world really runs on lithium.
Batteries, EVs, it's fundamental now.
Exactly.